Given the intuition, let's see how we can implement a quicksort algorithm in Java. So there are three methods that we want to go over. Two of them are to do with how we can split the original input list into two sublists. So one being where all the elements are less than or equal to the pivot, and the other list will be all the elements that are strictly larger than the pivot. And the third method that we want to go over will be the overall quicksort algorithm, which has to combine everything together according to how we sketch out in the earlier part. Let's take a look. And let me switch to iPad directly. These are the two methods I just briefly talked about how we can split the lists into two halves according to the pivot. I'll go over them in just a moment. And this will be the overall quicksort mechanism. You can see there's a sort method. And let me also show to you about the source code that you can also look into to play in the Eclipse. So if you go to the Eclipse under example recursion, you can see under the sorters, and now we got quicksorter to actually look at as opposed to merge sorter that we did earlier. So you should look at the quicksorter class over here. That one there is actually about a quicksort algorithm, which I'm going to go over with you on the iPad. And to really test it, you can definitely run the test quicksorter as JUnit test and see the test cases. Right? There's a source code. I'll rely on you to play with beyond the lecture. Let's now go back. And let's now take a look at let's say start with the two helper methods over here. So one is all less than or equal to. The other one is all larger than. And they are quite straightforward to implement. I just want to highlight the points you want to really see the correspondence with what we said earlier. Both of them, you're going to pass the pivot index, like where the pivot can be found, and then you will find the pivot value accordingly. So you can see for both of them, we actually got the pivot index over here, and also the pivot index over here. And this will be the original input list. Original input list that may not be sorted over here. And let's now highlight what's really the difference between these two helper methods. One will be we want to find out all the elements that are not exactly equal to the pivot. However, their value is less than or equal to the pivot value. You can think about this one here is really calculating this sublist that we spoke about earlier. And what about the other one? You know what? Let me be consistent with the color. This one here, maybe I will put green over here. Right? Can you see the green over here is corresponding to the green that we spoke about earlier. What about all the elements that are strictly larger than the pivot? In that case, if you go to the second method, all larger than, in that case, we can see all the elements whose indices are not equal to the pivot. And also their value is strictly larger than the pivot value, right? And in that case, you're going to put them into the resulting list and then eventually return it. Right, let's just take a look at one example run. The coding itself is really straightforward. I'm not going to waste your time. You can take a look by yourself rather quickly. Let's say this is the input list. Let's say. Right, so that's the input list over here. And it is not sorted at all. What we want to do is after all less than or equal to, it can actually generate the left list. After calling all larger than helper method, we can generate a right list. Let's talk about the first one. The first one here, let me use maybe the light green. All larger than or equal to, right? You can see I chose the color, this one here, to be the same as the left split over here. Right? After doing that, what should we get? We should really get all the elements in the original list that's less than or equal to the pivot. And what should be the pivot? Let's say the pivot that we choose is always the last elements, right? Just for illustration. What's the index for the pivot? 0, 1, 2, 3, 4, 5, 6, 7, right? So that one there is really index 7. So what we do is we're going to pass the list over here, and the pivot index will be 7, right? That's kind of minor detail. And what should we put in the left? It's going to be everything that's less than or equal to 50. It's going to be 24, and also 45, 17, and finally 31. Right? You can see this part over here is an example split of the left. Everything that's less than or equal to the pivot which is 50 in this case. What about the right split over here? That's going to be all the remaining elements. They are not equal to the pivot, but they are larger than the pivot. Okay, so what's going to happen is we're going to get 85, 63, and 96. 85, 63, and also 96. And let me put a color right. That would be the second list over here, right? That's really corresponding to the right split, right? So these two helper methods are rather easy to understand. We'll talk about their running time in the next part. Let's now talk about the sort method itself. Right? You can see here we got the two base cases. Let me just write it down. Think about these two are the base cases. Oh, let me draw a little bit larger. So these two are the base cases for the recursion. Right? You can see when the list is empty or when the list contains only one element. In that case, it will be sorted automatically. And this part over here nicely corresponds to the intuitive ideas that we went over, right? Remember, on the previous page, I just put a zoom out version over here, right? Let's take a look quickly. So the pivot index, we always choose the last index. Let's say that's the index for the pivot over here. And then the pivot value is going to be whatever value that's at that particular index, this value over here. The left is going to be calling the helper method by passing the pivot index and the list. That one is going to return the left. This will be the left, right? So you can think about this part over here will be the left. Right, let me make it a little bit thinner. This will be the left, and the next part will be the right. Right? Left will be returned by all less than or equal to, and also the right will be returned by all larger than over here, right? The left and the right, but not sorted yet. So that's why we have to recursively call the sort over here on the left and on the right, and magically it will work. Magically, the left and the right, the sorted left and sorted right. So you can think about this part over here. Let me just write it down. This will be the sorted left, and this will be the sorted right. Once we got these two sorted sublists, and we're going to simply concatenate them together. Just say add or, add and add or. We'll just get a sorted list. You can think about which each of these individual methods over here is simply constant amount of time. We're simply just trying to put the sorted list together, right? If you think about, if you try to implement this using a singly linked list, you're simply setting the next reference to be this and setting the reference next reference to this, right? That's definitely constant amount of time, right? So you really want to see the close correspondence between the Java code to the conceptual sketch that we had earlier. That's really what I want you to see. Let's now try to trace how the QuickSort is going to run at the runtime. Let's do that quickly, and then we'll move on to the last bit of the discussion about running time. Right? Let's now say this is our input list, and the assumption is we're always choosing the pivot as the last element in the list. Right? And there's a reason for me to choose the red color for the split, because the split is actually more expensive operation that we have to go for each recursion, and the concatenate part is going to be cheaper. On the other hand, if you compare what we did in the merge sort, in the case of the split for the merge sort, it's going to be the cheaper one, and when we try to merge, it would be the more expensive operation in the merge sort, right? You really want to compare and contrast the merge sort versus what we're talking about now, the QuickSort. Right, let's now do it. So once we have chosen the pivot over here, that will be 50, right? This will be the pivot. We're going to split the rest of the lists over here to the left and the right. And what's going to happen is we're going to call the larger less than or equal to, and also the larger than methods that we just went over. So we're going to split. So let me do that. So we're going to split to the left and also split to the right over here. Okay, so let's now do this. So if you split to the right, so what will be less than 50? We got 24, we got 45, we got 17, and also we got 31. And what about the right? The right will be 85, and then 63, and then 96 I believe I cover all the elements. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Good. And we are going to recursively sort the left before we can return back to here, right? Let's try to recursively sort this one. And we're going to, again, choose the pivot for recursive call because the same block of code is going to be run over here. In which case, we're going to start from the beginning, choosing the pivot, right? So choose the pivot over here. So 31 is going to be the pivot. And we're now going to split this left split to the left and also to the right. The left is going to be all the elements less than or equal to 31. So we got 24 and then we got 17. And the only element that's larger than 31 would be 45. Right, and then we're going to recursively sort this left split over here. And for that one, we're going to choose a pivot. We haven't reached the base case yet, so that'll be the pivot, 17. And once we have chosen the pivot, we have to do the split. All the elements less than or equal to 17, and all the elements larger than 17. What about this list over here? Well, there's no element that's less than or equal to 17, right? For the remaining elements. So it will just be empty, which is a base case, of course. And then we're also going to have on the right, all the elements larger than 17, which will be 24. This is one base case. This is just another base case over here. And this is a sorted list. This is also a sorted list. And now, in order for us to actually return, because now we're both reaching base cases, how do we return? We have to concatenate the three components together. So how do we concatenate? So we have to do concatenation, right? Let me just say concat. Concat, in this case, empty list. And also the pivot, which is 17, and also the 24 over here, which is the right list. That'll be 24. And what would that be? That would simply be just 17 followed by 24, right? So that would be, let me just use the purple over here. Maybe use this. So ultimately, we're going to get 17 and also 24. That would be the sorted list over here. All right, so let me just recap very quickly. That's really important. We're going to do something very similar for all the other recursive calls. Once we have reached this base case and also this base case, they will be sorted individually automatically. And then we're going to do the concatenation, which is exactly what has been specified over here. We're going to concatenate the sorted left, the pivot value, and also the sorted right. Right? You can see the sorted left, which will be empty in this case, the pivot we have chosen, and also the 24 in the list. And that's what we got so far. And we can resume to sorting the right split over here recursively. Well, in that case, it's just a base case, which will be just 45. So I'm just going to write this element here is a singleton list over here. That's actually sorted. Right? Let me just write the 45 over here. And that one there is a sorted list. Now we got a sorted left, we got a sorted right, and also the pivot. So now we can return by concatenating. So we're going to concat over here. Concatenation. And what should we concat? It would be the 17 and 24. This list over here, the pivot 31, and also this right list over here, which is 45. Right? Let me just highlight it so you can see a little bit more clearly. So this one here, 31 and also 45. Once you concatenate them, we will get the following list that should be sorted, which will be 17, 24, 31, and 45. That is the sorted list overall on the left. All right, you can see now we are done with the sorting on the left split from the original list. And we should really do the right as well, right? Why don't we do it quickly? But of course, you can feel free to actually try to do the same tracing from scratch on your own. Let's try to do that. For the right split from the original list, we have to choose a pivot again to recursively sort it. So we're going to choose 96 over here. That'll be the pivot, right? What should be the left list? The left split is going to be, so we're gonna split one over here, split again, and also split again, right? In that case, we're going to get all the elements less than or equal to 96, which would be 85 followed by 63. 85 followed by 63. And notice that the same order has been preserved over here. There's no sorting just yet. And what about elements strictly larger than 96? Well, nothing, right? Empty list. This will just be empty, which can be sorted right away, but we'll get there a little bit later. And we want to now recursively sort this left split again. The pivot is actually 63. Are there any elements less than or equal to 63 in the remaining element? The answer is no. We only got 85 left. And also the right split over here will be just 85 over here. Right? You can see this is sorted, this is also sorted, so now we can do the concatenation. Right? So now we can concatenate over here. What should we concatenate? Empty list over here, pivot, and also 85. That one is actually going to give you, I'm going to write it down directly. That one will be simply 63 and then followed by 85, right? You can see. But just don't lose the big picture. That's exactly how the QuickSort actually works. And this one over here, the right split is just empty, so it's sorted right away. And now we can return by concatenating further. So we can now do the concatenating. And what should we concatenate? Well, it will be the left sorted list, 63 followed by 85, and the pivot, and also this list over here is just empty, right? So this one here, let me just highlight it so it's easier for you to see. That one there is actually going to be 63 followed by 85 followed by 96, right? So that'll be the sorted list. Now we got a sorted left, we got a sorted right, and we got a pivot for the original list. What should we do? As an ultimate step, we want to concatenate them together, and then we can draw the conclusion. We want to do concatenate, right? Let me write it down directly. This final concatenation is going to return us to the ultimate sorted list. It's going to be the left followed by the pivot followed by the right. Let's now write it down. 17, 24, 31, 45, the pivot 50, and then 63, 85, and 96. This is the ultimate sorted list over here. That's the answer, right? It will be very important for you to understand the individual steps, especially the different phases for the QuickSort. Again, when you do the split from a list into left and right, that will be the expensive part, as we will see. However, once you invoke the recursive routine on the left and the right, once you get a sorted left and sorted right, the remaining part will be quite cheap. In that case, you can simply concatenate the sorted left followed by pivot followed by the sorted right. You want to see exactly how. Alrighty, so that's about the complete tracing, and the final bit for the discussion will be the running time for the QuickSort.